Hello, physics family. We're going to be talking about Coulomb's law today, which is basically how attracted or how much repulsion is taking place between two charges. And you can see a lot of similarities between that and gravity. So let's go. To start with, talking about electrostatic forces, we are fully aware that you do not need to have two objects touching in order to feel electrostatic force. We know that oppositely charged particles attract and that the same type of charge is going to repel. And we saw that with our labs, with the pith ball and the negatively charged rubber rod, etc. But when we really start to look at how strong are these attractions or repulsions, which is a force, a push or pull, then we're going to start to see a lot of similarities between that and gravitational force. And again, those are just two objects because of their charge that are attracting or repelling each other. As long as an object has a charge, we know that it can exert a force on both a charged or an uncharged object. And we know that because of conduction and induction as well. So let's look further into that. Here's a delightful picture of Coulomb himself, but his law basically was a formula for electrostatic force. Now, if we are familiar with the gravitational constant that we just got done studying about with our gravitational constant times mass 1 times mass 2 divided by the distance squared, we know that formula. We'll take a look at that, and it's very similar to what the force of electrostatic attraction or repulsion is. It is still a constant, but in this case, instead of capital G, it's this one down here, the electrostatic constant, which is coming in at 8.99 times 10 to the 9th. And if you look at all the units, of course, there's newtons, meters, and coulombs, but we know when we use constants that after everything cancels out, we end up with a certain thing that we're looking for. In this case, if we're solving for the force of electrostatic attraction or repulsion, we're looking for newtons. Now, to focus more in on this equation, if we look at Q1 and Q2, those are the charges that are going to be associated with what objects we're looking at. Of course, we already talked about K. K is this constant, 8.99 times 10 to the 9th. And r squared, which is similar to d squared, the distance squared, it's just the distance between the two objects. So you can use a d or an r there, but that, in fact, is the distance. So when just pulling apart this equation, there's really not much difference from that in the gravitational one, except that in gravity, we're concerned with mass to determine the size of the force of gravity. And with charge, electrostatic force, we're concerned with the charge that's affecting the force. Think back to gravity. If you are at the surface of the Earth, your acceleration is about 9.8. But if you go twice the distance from the center of the Earth, you now have 1/4 of the gravitational pull, which means 1/4 of the acceleration of gravity. And that's because of the inverse square law. 3 times, it's 1/9 the force of gravity. 4 times, it's 1/16. Well, believe it or not, electrostatic force is very similar with the distance. As it increases, it creates this inverse square rule, and we will talk about that. That same similarity, if you increase the charge, for instance, if we're looking at this equation right here, say you double the charge of 1 and triple the charge of charge 2, no matter what happens to all the other stuff, you're doing 2 times 3 times the electrostatic force, which means you'll have 6 times the electrostatic force because you double and triple the charge. Now say that you are going to triple a distance. So 3r squared, k q1, q2. Well, what is 3 squared? 3 squared equals 9. But 9 is in the denominator. So it's really the same as 1/9 of the electrostatic force. So again, that inverse square rule or law holds true for finding electrostatic force, just like you would for the force of gravity. All right, let's look at this problem. We want to find the gravitational force and the electrostatic force between a proton and an electron. So first of all, if we want to find the force of gravity, we know that the equation for the force of gravity is our constant times mass 1 times mass 2 over the distance squared. If we want to find the electrostatic force between the proton and electron, it's very similar with a constant with charge 1 and charge 2 and the distance in between them. So let's hash this out. First of all, the force of gravity would be equal 6.67 times 10 to the negative 11th is your big G. And the masses, if we look down here, the mass of a proton and the mass of the electron are right here. 1.67 times 10 to the negative 27th. And 9.11 times 10 to the negative 31st. And what we have is we're going to put that over our distance, which is 5.3 times 10 to the negative 11th. And don't forget to square that. Now that setup looks very similar to if we did it for electrostatic force. I'm going to do that up here, though, to give me plenty of room. My electrostatic force is going to be equal to my constant, which is 9 times 10 to the 9th, times my two charges. Now my charge on the proton is positive 1.6 times 10 to the 19th, negative. And my other charge for my electron is negative 1.6 times 10 to the 19th. So I'll put that right here, negative 1.6 times 10 to the negative 19th. Sorry for running out of room there. That's all multiplied together, divided by the distance, which is 5.3 times 10 to the negative 11th. And of course, that's squared. Now, though that's maybe a little sloppy, and I apologize, if you look at the difference between these two equations, they look fairly similar. The only difference is they're constant, and for gravity, we're focused on mass, and for charge or electrostatic force, we're focused on charge. But when you look at them, they're both going to have a fairly small number when you solve for it. The answers to both of these, you get force of gravity is 3.6 times 10 to the negative 47th newtons. Obviously, an incredibly small amount of gravitational force between a proton and electron. Their masses are ridiculously small. But if you look at the exponent here is to the negative 47th newtons compared to up here to the negative 8th newtons for electrostatic force, you can see that their attraction to each other is quite strong because of their electrostatic force. And the negative here in the answer, negative 8.20 times 10 to the negative 8, tells you that they're attracted to each other because they're opposite charge. If it's a positive number, it's a force of repulsion then. Something to keep in mind. So if it's negative for an answer, we are attracting, and if it's positive, we are repelling. All right, so this concludes our idea of Coulomb's law and that charges create an electrostatic force. They can be push or pull, but as long as we have charges associated with them, there's definitely a force that's either, pushing or pulling, like we just said. So hopefully you could follow that and see the similarities between that and gravity. Best of luck. We'll try some practice problems to make sure that we can knock this out and see the difference between attraction and repulsion, and also just how strong particles are when they come across each other. Thanks for listening.